Besos,
Yes.
before you start the class, is it possible to extend the time for the assignment 7, please?
Assignment 7, that is the repeat and measure one.
Yes, I want to do that, but for some reason I was not able to see those videos. So if you allow, I want to do that. Just want some favor. Thank you.
Well, go ahead and do it and we'll see. I don't want to give a blank extension because I already gave 2 weeks for that, but I mean go ahead and work on it and then we'll see how that goes. Because yeah, if y'all remember, so on our syllabus, so we do accept late submissions up to a week, although you do lose 1 grade if you turn in late. But after a week, then we don't accept any more. I mean, I don't accept any more submissions. So let's go with that first, and then we'll see how that goes. I think that's where I'll put that.
Thank you.
Yeah, thanks, very full. Okay, so today, we last class we were doing the feature engineering exercise, and we have not finished that. So my goal today is for us to finish that first, and then after that, we're going to be talking about some multivariate analysis, and some issues that may arise from multivariate analysis, and some of the ways that we are going to try to overcome that. And we're going to look into a couple of different analysis of multivariate data. And these topics are bringing us closer to machine learning. As we're seeing first how to find open source data, create a lot of variables in our data frames. Perhaps you don't have to create from open source. Perhaps on your own research, you already have a lot of variables that you're trying to make sense. And then we're going to start talking about multivariate models, which most of these machine learning models are really useful and used when you have multivariate scenarios where you have a lot of variables that you're trying to understand what are the main drivers of your predicted or response variable. Okay, so coming to back to today's exercise, we stopped at this point here where we were about to so the goal, I guess, from my side, let's see, I don't think we were pulling, yeah, we're not pulling open source data here. So you can just go ahead, and if you want to go to the chunk that we stopped, which is this one called FE month sum wide on your table of contents. If you want to go there and just play or run all chunks above, so you create all the objects in your environment in case you close this RStudio window. And then we're going to take a look at what we have right now. So FE month sum is basically what we're going to be working with. So this data set here has 8,376 rows and 10 columns. And the reason why it has these many rows is because it's all of our 698 site years times 12, which are the months of the year, right? So right now, month is as a column right here. And then each one of our variables or weather-related variables are a column. So my goal here is that whenever we feed this data into any model, but especially machine learning models, at least the models we're going to be using, we need to have this month information as part of the column name itself. So instead of having, let's say, a mean day length in seconds and each row being a different month, I need to have mean day length underscore month. So let's say underscore January, underscore February, and then each column be that variable for a different month. So the model can tell you, well, mean day length in January is more important than mean day length in, I don't know, July, or maybe the opposite would be most important actually for crops growing in this part of the world. But so we want the model to be able to tell us not just the variable, but what month or what time period that we summarize, which in our case was month, that variable is more important. So basically what I want to do is go from these 8,376 rows back to 698, where each row again becomes a site here, and then you have all these columns related to weather across different months. So that's what we were about to do on this next chunk here. We're going to basically place that month information as part of the column name and make it from long to a wide data frame. All right, so there's probably a couple different ways of doing this, as always, and I want to show you one of them. So if we just print again FV month sum, which is the one that we're just seeing, my goal here is to do the following. I wanna create a column or many columns that are gonna have this, each one of the current column names related to weather, and then give an underscore and then the month name. So we already have month name, or at least the abbreviation in this column right here. So one way that we can achieve what I'm telling you is going to be to do a pivot longer on the weather variables themselves. Because then once we do that, we're going to have two new columns where one of them is going to be weather variable name. So then we're going to have weather variable name as one column, and then the month name as another column. Then we can combine both of them into one third column and pivot wider again with that column that we just created. I see some confused faces, I guess, but let's try to implement that. I think it's going to become a little bit easier once we see it. All right, so with what I just told you, then our immediate next step here would be to basically pivot longer all the actual weather variables. So let's go ahead and use a pivot longer. So the columns that we're going to be pivoting are basically all the weather variables, and because they're all in sequence, so starting on the first one is mean day length in seconds. So we can type that and then give a colon. And then the last one is some precip in millimeters. We just do this and run that. Now we're basically going to have a lot more rows. So 50,000 rows, because now we have our, so it's still year site as we had before. We still have our month abbreviated, our predicted variable of strength in grams per text. But now we have a name column that has all the previous weather column headings under a single column, right? So we've used pivot longer before. So I guess the way that it looks right now shouldn't be a surprise to you. But now notice that we have this column that has the variable name, and then we also have the month abbreviated column, which has the month name. So the next step is going to be to create a third column that combines both of those pieces of information to one, and then pivot wider by that column. So the next step here, let's give it a mutate. I want to call this column var name. And let me ask somebody, if somebody remembers how, I mean, and again, maybe there's a couple of different ways of doing this, but how have we been combining two pieces of information and given a separator in between them in the past?
Using page zero.
Page zero, right? Right, great. A lot of you were thinking about that. So page zero is what we need. So we're going to say page zero, and then name is the current name of the column that has all the weather variables. And then let's give it a, in quotation marks, an underscore, that to be the separator. And then the column that has the month information is called month ab. So if you run that and you print now FE month sum wide, now we have this column. So this var name, where we have the weather variable name underscore the month that is coming from. So now that we have this new column var name, we can basically pivot wider using this new column, and then having a lot of columns now where each one of them is going to be a variable, a weather variable underscore, and the month of that variable for each one of the side years. Before we do, well, I think I'm going to try to do the pivot wider right here and see what happens. But I'm anticipating that an issue is going to occur, and I want to show you how to fix that. So let's go ahead, give our pipe. Let's do a pivot wider where our names, so names from is going to be from that new column var name that we just created. And values from is going to be from the column that is called value, which was the one that we got after we did the pivot longer. So once we do this, we should return back to 698 rows. One row for each side year, and then one column for each combination of weather variable by month. But that did not happen. And the reason for that is if you look, so it did do a pivot longer, but the thing is that we just got a whole bunch of NAs. Like it shouldn't be doing this. It should be, each one of these values should be on the same column associated with a given variable. So, and it's kind of weird because it doesn't really give us an error or a warning. It just doesn't give us what we were expecting. So this has happened to me many times when I'm pivoting longer or wider. And what is going on here is basically that we have some columns right before we did the pivot wider. There are some columns in that data frame that do not allow for it to pivot wider and have a unique combination of the other columns. And this, I guess, well, it took me to figure out what was going on. It took me a while to really understand what was going on when I first came across this problem. But what is going on here is basically that we have the columns. So after we pivoted wider, we still have the column name and the column month abbreviation. And these two columns, because we use them to create the third column, which is var name, and because name and month abbreviation are still in the data frame, when you pivot wider, it's still stuck with keeping those values there while pivoting wider. So it does not allow the data frame to be clean and not have those placeholders for name and month abbreviated as it pivot widers. I know this can be a little bit confusing just looking at it, but I guess the main point that you would realize is that, so first, the number of rows did not change. It's still the same as before we pivoted wider. So that should be a warning for you that if you pivot wider, you should have a different number of rows. That did not happen here. And then as you go into the data set, you realize they have a lot of NAs here where you really should not have NAs. So the fix to this is basically to remove that column name and month abbreviated because they're the ones keeping the pivot wider to be successful. So right before the pivot wider, so if you come here after the mutate and before the pivot wider, let's do a dplyr select and then say minus name, minus month, ABB, and then feed that into the pivot wider with a pipe. So if you do this, and now you print it, now we have 698 rows. And our columns now are, they don't have NAs in them. They're basically what we would expect. So notice that we have, so for January, we have mean day length, solar radiation, Tmax, Tmean, vapor pressure deficit, and some precipitation. And then goes to February. So February, day length, and so on, right? Until for all the months of the year and all the variables, the weather variables that we had in this data frame. So basically we end up with one row per side year. And then we end up with 75 columns, all related to weather variables summarized on a monthly scale for each one of the side years. All right, so just to wrap up this chunk here, the next thing I want to do is basically, I want to round these weather variables. So some of them have as you can see, like some of them have a lot of decimal points, really not necessary. So I want to basically round all of these weather month variables to have 1 decimal point. And because we're going to be applying that to a lot of columns, basically we're just not going to apply that to ear, sight, and strength. But then everything else, all the weather variables, we're going to be applying this round. So to do that, we're basically, I mean, we can actually include a strength as well. We could do that. So just 2 variables. So 73 variables we're going to be rounding. Again, there's a couple of different ways you can do that, but to make sure we do this in an efficient way, let's give it a pipe here, come after the rounding to 1 decimal point. We're going to use a mutate. And here we're going to use a function called across. So we've used this function before. So every time you're applying a given function to many columns and you want that to be done in a more automated way, across can be used. So the function is called across. Inside of it, it takes 2 arguments. The first one is which columns it will apply whatever function, and the second is what function you're applying to those columns. So on the first argument here, we're going to give it the position of those columns. So basically, starting in position 3, which is strength, all the way to position 75, which incorporates all of those weather variables, we can use the C function and say 3 colon 75. So this is just by position and not by name. If you get outside of that C, give it a comma, and then we're going to give what is the function we're applying to all those columns, which is going to be the function round. So we need to give the tilde here and say round, give it a dot just to represent each one of those columns, and then comma 1. So we're saying round each one of those columns that we're selecting to 1 decimal point. So if you run this and you print it, now starting from column 3, which is strength, all the way to the last column, you should have just 1 decimal point across all those numerical variables. All right. So this is basically the data set that we're going to be using from this point on. And at some point later on this exercise, we're going to save this data set to file just so we can reutilize in the future exercise. And I was going to ask if anyone had any question at this point. I see that Comfort has a question. Go ahead, Comfort.
Yeah, I just wanted to ask that, is it really compulsory to do the C, then put the brackets 3 ratios colon 75? I tried it without it and it kind of worked, but I don't know if it's just better practice to do that.
Yeah, we can definitely, I don't remember exactly from when I developed the script, if that was necessary. Yeah, I think maybe it was not necessary. Yes, thanks, Comfort. Yeah, I don't remember now. Maybe when I wrote this script, maybe the C was required for some reason, or maybe it was just what I tried initially and it worked, and so I just kept it. Yeah, but I guess it seems like we don't really need the C in this case, and it's just one of those cases where perhaps you can do the same thing in a couple different ways. So maybe that's a good point here. I would imagine that like if we try to give the column names as well, we could probably give strength all the way to the last column. I think that would also work. So there's definitely a couple or a few different ways that we can specify here. But thanks for pointing that out. And I think this is also interesting that I do encourage you all that if you have a question that's easy for you, like if you're gonna think of it like if you have a question that you can try yourself and find out if that works or not, I encourage you to do that because that's what programming is about, is kind of figuring things out by trial and error a lot of times, right? So, and I think you did that, Comfort, right? So I think you did try without the C and it worked. So that's definitely something I encourage you all to do, is if you're curious about something and related to the code, go ahead and try it. And if it doesn't work, you just undo it, right? There's no harm in that. Awesome.
I think,
Yeah.
yeah, I think the C is required if we do not just specify 75. So for example, if we just use n calls to indicate the last column in the across function, we would use C. Since we're specifying the column numbers, that's why it's working.
So,
But
Shakir is saying like if we were to do like in call, is that what you mean?
yeah.
Yeah, let's see. Yeah, I mean that we can quickly try that out. It looks like both worked actually. So, but anyways,
Oh,
yeah,
okay.
I guess the thought is just that we can definitely do the same thing different ways. And you know, I don't particularly expect or enforce that you do a specific way. As long as you get to the right answer, that's what matters, right? In real life, that's what matters. So yeah, many ways of getting to the same point. All right, any other questions about this before we move on? All right, I don't hear anything, so I'm gonna move on. So right now, as we just mentioned, we have 698 rows because we do have 698 site years. And each row now, so all the weather information for each site year is represented within a given row because we did the pivot wider, right? So let's say if we were to take Altus, Oklahoma, 1980, all the information about Altus, Oklahoma, 1980 is within that first row, right? All that data on the first row is just for that site year, and each site year has their own row and all information associated with that. So I do want to do a second round of EDA here. You know, so we just created a whole bunch of new variables, and I do want to explore them and visualize them in a different way. Let's see here. So one, I don't know, this is a really cool package here for plotting distributions that I want to show you next. At least in this class, I don't think we've seen this. So I don't expect you to have this package. If you try to run a library, ggridges, and it does not load, says you don't have the package, I left you the code right above it for you to install that. So if you have to install, go ahead and install. Make sure that after you do install, you either comment off that line of code or just delete that. And once you do install, we're gonna load that library and we're gonna make some plots. So basically what I want to do here is I'm going to do for one of the variables first. I want to basically plot the one of these weather variables, and I want to show that as basically as a density plot. But what ggridges does for us is it does density plots in a kind of like a stacked way, which I think once we do it, you're gonna see what I'm trying to say. So once you install ggridges and you load that package, let's go ahead and call ggplot to begin our plot. We're going to say data equals to this object that we just created, which is FE, or actually, we're not going to be using that one quite yet. We're going to use, now that we're just creating one plot, we're going to use the previous version of data frame, which was called FE underscore month underscore sum. If I print that here just for us to see, what I want to make out of this plot is show the mean Tmax in Celsius, which is this column right here, on our x-axis, and then the month on the y-axis. So right here on the ggplot call, you can give it a comma. Let's call a yes. So the x I want to be mean underscore Tmax dot C. That's the column name for the mean temperature, maximum temperature. The Y I want to be month ABB. So the abbreviated month name. And now there's going to be something very specific because we're using ggridges. I want our fill to be equals to stats of X. This may not make sense to you right now, but it will make sense once we make the plots and what that means. So if you come at the end of that ggplot, just add a plus. We're gonna call geom underscore density. Let's make sure I loaded. Geom density ridges. So let me type it. This is gonna be easier. Ridges gradient. Let's just go ahead and run that and see what happens. Okay, so this is basically what it did. It took all the column mean temperature max in Celsius, and it has month on the y-axis. So this is basically the data for each month across all different site years. So if you imagine each one of these density plots are basically data for all site years for that variable, which is mean Tmax, and that specific month. So in other words, this is the distribution of mean Tmax for each month across all site years, right? So this is a pretty cool way of showing, especially in this case, we're showing a variable that changes over time, and that time variable is one of our x's, right? So you really see this shift, like as you know, as the month progresses over the year, you see this shift overall of the mean Tmax, but also the distribution across all the site years as well within the month. So this is basically what ggridges does for you. There's many other ways of creating similar plots. So if you enjoy this type of visualization, I would suggest you take a look at the vignette of the ggridges package online. It has many great examples of how to do this as well. I do want to change a few things here just to make this look nicer. So one of them here on the ridges gradient, it has many arguments we can change, but the one I want to change here first is scale. So I want to say scale equals to 3. That is going to change. This basically, it decreases the distance between the lines across, or the ridges, the density plots between each month. So it just made that distance a little bit closer. Also, I want to, so if you notice right now, for all of the months, we have the tail of that distribution is basically going all the way from 0 to, I don't know, 46 perhaps. I want that to not be the case. I want it to say that whenever the density of that density plot is less than a given threshold, to just not show that line. So to do that, we come here on this function. It has an argument for rel min height. I want to say 0.01, 0.01. So if we do that, it just kind of cuts down the tails of that distribution a little bit for us. And then a couple more things I want to do here is I want to change this to a different color scale. So I want to change to scale underscore fill underscore Virides C for continuous. I'm trying to think if in this class we talked a lot about Virides scale. Did we? Did you already talk about? So just as a reminder, so Virides is a collection of color scales that are colorblind safe. So I always prefer to use them. And within that Virides family of scales, it has a few different ones that we can change by changing the option. So I guess, well, before changing the option, if I just run that to you, it is this color scale here that's very typical and a very popular color scale because it is probably one of the most popular colorblind friendly color scales. But it has others, and there's one that I think is gonna be more intuitive because we're showing temperature data. So we can change the option here, and it has many options going from A to F, I believe. I want to change this option to C, which is the magma option, I believe. So it looks like that. Now it is weather related. I see some smiles. It's pretty cool. The outcome is pretty cool. So it has that scale from, basically purple colors meaning cooler, and then orange meaning warmer temperatures. So pretty cool for our case. And then lastly, I just want to, so if you think of it, this legend that we're seeing here is basically just the gradient of temperature within the plots, which I think is not very useful to have this legend because we already have temperature on the x-axis anyways. So I just want to remove this legend from here. You can do that by calling the theme function and just say legend dot position equals to none, and that basically removes the legend for you. Mhm. Yeah, so this, I think, as I hope you're realizing, ggplot is probably the best library for plotting across languages. I don't think even Python has something that is as powerful and intuitive as ggplot. So really, ggplot has a lot of really nice plotting functions, and this is one of the ones that I think can be really, really cool to show your data, using the ridges plots. Okay, so now the next piece of code here that we're gonna work with is basically just repeating all this for all of our variables. So we just did for one of them here. We just did for mean Tmax. I want to do that for all of our variables. And just to perhaps try to not confuse you here. So we're using for this plot FE month sum, which still has those 8,000 some rows. We still have month as a column here rather than being month as part of the other column names. And we're going to be using this just for plotting purposes because this shape of this data frame is more helpful for us to make these plots. But really, at the end of this exercise, we're going to be exporting to file FE month sum white. That's the one that we'll continue using in the future exercises here. So just don't want you to get confused. Even though FE month sum white is the last thing we created, we kind of went back to make some plots based on the previous version of that. But in the end, we will be exporting that latest version. Okay, so on this next piece of code here, I'm gonna start off here, then I'm gonna ask for some help. So we're gonna start off with that same data set, so FE month sum. So my goal now is to create the same plot here that we just did. So this plot, but for every single weather variable. So remember that month is still a column in this state. It's not as part of the column name. It's still a column, right? So we're starting off with FE month sum. But I want to make this ggridge plot with all of our weather variables, which we have, I think, 7 or 8. So I want to do 7 or 8 plots like this on a perhaps somewhat automated way. In this case. So I think there may be a couple of different ways we could do this, but any thoughts on how you would accomplish that?
Create a function.
Okay, we could
We
create
can use pivot longer.
Yes, it's gonna come down to pivot longer for sure. That's gonna be our first step. So let's go ahead and do a pivot longer. So basically, I want to pivot longer all the weather variables so we can start off on mean day length S. Give it a colon and go all the way to some precip millimeters. I just print that so we can see how that looks like. So we have 50,000 rows, and then now we have a column for name. All right. What's next?
Is it going to be facet for some reason?
So
We can use group by year, I guess.
I think we have a couple of different ways of, or maybe more than a couple, but at least there's one that I developed that involves the map function. But now I'm looking at my own code and I'm thinking, why did I not try a facet? Because I think a facet would work without having to do a map function. So maybe let's try that. Let's go ahead and try to do a facet instead of what I had here on my original code. So let's plug this right into a ggplot. So actually what we can do is basically, if you go back to the previous chunk, you can just copy all that and we can edit that. So if we just copy all that and then you come here and paste right here, I don't think we need to give the data argument. So I'm deleting the data argument because that is implicit coming through the pipe. On the X, we're gonna have to change, right? So now, because remember, what ggplot is seeing is whatever is coming up until right before that pipe. So right now we have a name column and a value column. So what should go on X? Do you think name should go on X? Any other thoughts?
Value.
It should really be value,
Value.
right? Yes, it
Yeah.
should be value because name only has the names. We want the actual values to go, even though it's kind of, it's not as intuitive to think of it, but yeah, we want value to go there. And I think if we just come all the way to the end here and add a plus and ask for a facet, I think that's going to work. So maybe let's do a facet wrap. We can give a tilde, and what is the column that we facet by?
Name.
Name, right? Yeah, this is where name would go. So name, and then we can say scales. Let's see, is that scales or scale? I think it's scales. Let's try. Equals to 3. Let's see, on my code is giving me, no, I think it's working. All right, let's try that. Okay. So it kind of worked. I think now that I'm looking back into the code that I have on my cheat sheet here, I think the reason why I did not do this is because the color scale doesn't, I mean, it applies for the first column, but because the units are so different, the color scale does not translate well to the others. So I think that's why I have on my original one to do a map instead. Okay, so we can do that. We're just gonna have to do some adaptations to this code. So the goal here is gonna be basically to use the map function to create one plot or first to create the data frame just for each one of those weather variables, and then create a plot based on each one of those weather variables. You've done this with iteration exercise before. So we're gonna have to do that combo of group by and nest. So if we go ahead and do a group by, we need to group by the column name, right? That's the one that has the separator of our weather data. And then if we give a pipe, we're going to use the function nest. I want to run until here so we can understand what this is doing. So if I run just there, I did not add a pipe to connect with ggplot yet. And I just want to print final plots so we see what it looks like. So now we have 6 rows because we have 6 weather variables under the column name. And then if you remember, this is that nested data frame style where we have a column here where each cell under that column is an actual full data frame, right? So the first row here under data is basically all the data related to mean day length in seconds. So if I just pull out the first cell under data, so final plots, $ data, double brackets 1, I get 8,000 rows with all the data just for that column, which is for day length. Right, so I just want to come back here. So this first cell here actually is a data frame with over 8,000 rows, and the same for each of the other ones. But now that we have each data separated by weather, we can basically create this ggplot for each one of them, and then the color scale will be different for each one of them because it's a full different data set that ggplot is running on, rather than one ggplot call running for all plots. So right after that nest, we're going to give a pipe. We're going to give a mutate to create a column that I want to call plot. So here, we're going to basically use one of the map functions, and I want to use two arguments here. So one of them is the data frame itself, because we need to pass that for ggplot to make a plot. But I also want to have the name of that variable to be passed as well. So we can add the name of the weather variable as a title, so we know what weather variable is what plot. Because of that, we're going to use the function map2, where we're passing the arguments data and name. Data, name. You give it a comma, break line. We need to give the tilde here. Basically, you can just copy this ggplot all the way. Well, sorry. So let's do this. Remove the facet wrap. So remove facet wrap and plus, because within each one of these data frames, we're not going to be faceting, right? It's already just that weather variable each data frame. So I deleted the plus and the facet. So go ahead and copy that ggplot all the way to theme, to closing that theme, and actually cut, I guess. You can come and paste right after the tilde that we have inside the function map2. So we're going to have to change a couple things here. What are they? To make sure that this works. So remember that map2 takes two arguments, right? The first one becomes .x, the second one becomes .y. So right now we're not using neither of them in this ggplot call, and we have to. So what would you do?
So x equal to dot y.
Sorry, can you say that again?
It will be x equal to like we have to assign two values at the same x equal to dot y.
So on the map2, we don't have to say that specifically because it's already implicit. We do have to specify what you're saying on the pmap function because that takes an unlimited number of iterating columns. So right now, I mean, we could try to run this if you're curious. You know, I don't think it's gonna work though. So he has saying a lot of stuff here, and it's not very clear what the problem is, at least not from the error message. But I know that a ggplot needs a data frame, right? We're not specifying yet a data frame here. So we have to have here come on the ggplot call and say data equals to what? X.
Dot x.
Yes, .x, right? So .x is that iterating column that is a placeholder for the first argument, which is the data. So if we do that, I think now it would run. I think it would work. We can run it and then check final plots. So we do have our plot column that is a ggplot object type. And if I just pull the first plot here, just for us to look into that, this is what it is. So this is for SIP, maybe, I guess. Oh no, day length. This is day length in seconds. Yeah. However, the reason why we use map2 is because we could then add the variable name as part of the title of this plot. So how would you do that? If I come after theme, what function would you use to do that? Labs, right?
Labs.
Perfect. So we can say, actually, I think in my code here, I have the X. So right now, the X is just saying value. we can rename this to be the variable name. So basically we just say x equals dot y. So the axis title is going to be equal to dot y, which is the name coming through on the map2 function. So if you run that and you print the first plot, this is what we get. And now, if you remember, the issue we had when we did the facet is that the color of these density plots, it was not working across all the plots because it was basically the color was being skewed by day length, which is such a high magnitude of number that everything else was just blue, all the other plots. But now if you just come on the next chunk here and you run this, which is basically going to print each individual plot for us, now each one of them have their own color scale because they were developed fully independently from the other, right? So we have solar radiation, mean max temperature, mean minimum temperature, vapor pressure deficit, and then precipitation. All right. So this is basically what I wanted to show you, is just how you could create, many different ggridge plots for many variables in a more automated way using the map function again. Okay, so as I was telling you before, our goal here is to basically export this data frame. Yes. To this one. Well, I guess any questions or thoughts or code issues at this point? Yes, Comfort.
Yeah, it's telling me that object.y it's not found.
So what I would check is that you use the function map2 that you gave data and name, and that you gave the tilde here,
Yes.
and also that you added a plus here.
Yes. Okay, I understand now. Thank you. I wrote the labs outside of the ggplots.
Oh, yeah.
Yeah, thank you.
Yeah, absolutely. All right. Any other questions, thoughts, issues? Okay, so with that, with the end of this script here, that was for feature engineering, we basically did our feature engineering, at least the majority of it in this script. Now we're going to export this data frame to file so we can keep using in the future exercise that is coming up. So I think I left you the code here. You can just use the write CSV to export this to your data folder of this project. And here we have, I'm calling this weather month sum.csv. So make sure you run that chunk. And once you run it, you should be able to see now on your data folder. And just as a reminder, the FE month sum wide is the one that we do have 698 rows, 1 row for each side year. And then we have 75 columns, which are all the combinations of weather variables and month over time. Okay, so a quick summary of this exercise. We imported the original 7 weather variables from Daymat. We feature engineer a total of 72 secondary variables by applying a summarizing window size of month and a summarizing function of mean or sum. And this, again, we talked earlier about this, that we could have potentially used a different size window. It could have been maybe for the growing season. It could be maybe every 2 months. It could be maybe around a specific crop growth stage, which we don't have yet, but we could create that. And also the function could have been different. Maybe you were interested in the CV instead. Maybe you were interested in the minimum value or the maximum value instead of the mean. So there are different size windows and also statistical metrics that we can extract from any distribution. Then we did explore the actual distribution of those new variables and finally just exported that to file so we can use in the future exercise. All right. Since we wrap up this exercise, I first want to check if anyone has any questions. Yes, Comfort.
I know you mentioned it, but could you please remind me why you decided to use the map function instead of the facet wrap earlier on?
Yeah, so I guess I'm not gonna, well, it's not gonna be time efficient for me to show you completely, but if you go back to either the recording or maybe to the code itself, if we have used, so if instead of doing group by nest and map, if we had done straight into ggplot and used the facet, it did fast, so they did create the plots for us, but because the first variable, which is day length, has such a large magnitude of values, the color scale of all facets was shared, was the same color scale. And because day length had such a large magnitude of value, which is like on the thousands, it really skewed the color scale. So on the facet of day length, we could see the gradient in color, but on the other variables, everything was blue because it was just skewed on that color scale. So that was the reason why we did individual plots.
Thank you, sir.
Thank you. Okay, so what I want to ask you to do is go on our Git tab. You can stage your code, check your commits. Let's commit here and say finished feature engineering commit, and then push to your GitHub. After you've done that, you can basically close this this exercise. And so my plan here is I want to give you a 5-minute break, but before I let you take your break, I do want to tell you that we have a new exercise that during your break, I do want you to bring that or start that process. So I uploaded to GitHub, so you have to do a git pull on the class GitHub, a new or two new scripts. You can actually move both of them, or you can, well, you do a git pull on the class GitHub, but then on your GitHub, you're gonna create a project there first, as we've been doing. The name of the project is 10 underscore multivar. That's what I want to create on GitHub first. So on your GitHub, create a 10 underscore multivar, and then you copy that that path from GitHub, come on your computer, go on our studio, create a new project from Git, version control, Git, give that path, all that process that you have already done here 10 times or so. And then all that you need to do is then create your subfolders and move the two scripts that I uploaded today to the code subfolder. So there is a script for multivar and there's a script for k-means. Those are the two that we're going to be working next. So as you're doing that, I do want to put 5 minutes here on the clock. And once we come back, then we'll start our multivariate exercise. All right, so let's resume our exercise here. For those online, please open your cameras. Okay, so if maybe you already have this from when you created the project, but if you don't have that project open yet, go ahead and open it and launch that RStudio window for us to get started. And so in class, we're going to be working with the multivar PCA partial. That's what we're going to be working with for now. So please go ahead and launch that script. All right, so as you just noticed, for this data set, we use open source data from DayMat that we obtained based on the year and the location of the trials. We then did feature engineering and created from 7 variables, we created 72 new weather variables. So we have a lot of variables here that we're going to be using to try to predict cotton fiber strength, right? So we have a lot of variables. And so with that, we fall into this category of having a multivariate data set. So today or maybe not just today, but with this exercise, our learning objectives, let me just finish this airful, and I'll be with you in a second. So our learning objectives here are going to be to explore what is and when to use multivariate analysis. We're going to understand a couple of different types of multivariate analysis. And then this exercise specifically is going to be principal component analysis is what we're going to be learning and applying to this data set. We're going to import this feature engineered weather data that we just exported on the previous exercise. Use that to understand the concept of multicollinearity, why that is an issue, its effects on the analysis, and some remedies, which in this case here, the remedy is going to be, or one of them is going to be to run a principal component analysis to decrease our dimensions or for dimensionality reduction. Before I keep going, I think Arifu had a question. You want to go ahead and ask?
Oh, no, I'm facing a problem. It's saying I cannot pull the script. It cannot connect the server. Even I cannot go to the GitHub or anything. Maybe some internet issue. So just want to let you know.
Okay. Yeah, I mean, if you did not do a git pull on the 2025 DSA,
Arif,
Yes.
yeah, I think it will be internet issue. I had similar issue and then I just switched to using my phone hotspot and everything is working. So I don't know.
okay.
Maybe you are on internet company.
Yeah, it may be internet. I mean, but it's weird because if you're on Zoom, I think Zoom uses more data than just doing git pull.
Yeah,
So
but I cannot go any other pages. I can go to ELC, but I cannot go any other pages. I don't know. It's very weird.
Yeah, I think myself and Arif use the same server in our homes, so I think they have issues.
okay.
Maybe.
Yeah, I'm not sure if that's something I can help you with then. But I mean, if anything, the script is on GitHub. So even if you can access GitHub, then you could even just manually download from there if that's the case. But if that's not working, then I guess you're just gonna have to try when you have better internet. All right. Okay, so before we start talking about multicollinearity and looking to this data set that we just created in a few different ways, I do want to talk about some terminology here that we're going to be using. I mean, we've been already using some of these terms, but I just want to clarify some of them because I don't think we had a clear distinction, at least not in this class. So every single formula or every single analysis we run is going to take some form related to this, where we have a y variable explained by one or more x variables, right? So if you take this overall concept of this formula, y explained by x, a few terms here that we've been using. So especially when it comes down to experimental design, which was the first half of this course. We tend to call y as the response variable, right? So you say, well, what was your measured response variable? What did you measure? What is it that you're trying to explain? That is normally called our response variable or dependent variable as well. And it's dependent because it depends on the axis that you are using to explain that variable, right? So response or dependent variable are terminology more commonly used in experimental design type of analysis. And when it comes down to machine learning, you may start hearing a few different words. So maybe predicted variable. And the goal here is or the reason for why the terminology changes to how to relate to the y variable is basically because in machine learning, most of the time, our goal is to predict, is to make a prediction into the future, is to use unseen data and make a prediction on that, right? So in more machine learning type of approach, the y variable, we refer to it as the predicted variable. Now the x variable, so the right side of the tilde or the equal sign in the formula, is normally referred to as our explanatory variable or independent variable. Both of those terms, again, are more used in experimental design types of analysis. And when it comes to machine learning types of analysis, it's also referred to as a predictor variable. So if you think in our case, our predicted variable, our y variable, is cotton fiber strength. Our predictor variables, or x variables, are all those weather variables across different months of the year. So just wanted to clarify some of this terminology here, because we may be referring to y and x in any of these ways. I normally call y a response variable if it's experimental design, and a predicted variable if it's machine learning. And I normally call x variable as explanatory variable if it's experimental design, and predictor variable if it's machine learning related. All right, so then what is a multivariate analysis, or what is the structure that any multivariate analysis is going to take? Most commonly, that is when you have multiple x's, so multiple predictor variables in your formula. Something like this. So we have one y variable explained by multiple x variables. So a lot of variables on the right side of that tilde, right? So for example, it could be yield explained by precipitation, temperature, soil organic matter, hybrid, and so on. Sometimes a multivariate analysis can also be just multiple predictors, so multiple x's, but no y variable. So there's nothing on the left side of this equal sign. It's just everything is on the right side of it. And this is going to basically set one of the distinctions that we're going to talk about soon here, as far as supervised and unsupervised analysis. We're going to come back to this terminology in a second, but basically we have multivariate analysis where you're not trying to predict something specific. You're just trying to look for patterns on your x variables. So you don't have a y variable, you just have multiple x's. Also, I think something that was a question on a previous lecture of this class was that sometimes you can have multiple y variables as well as part of a multivariate analysis. So maybe you have multiple y variables explained by perhaps one or more x variables. So this would be the example of multivariate ANOVA analysis, where you may have, for example, yield plus biomass being explained as a function of precipitation and temperature. I think all the three, at least from my experience and what I've seen in the literature that relates to my field, this last one is the one that I see the least. Probably the one I see the most is the first one, where you have one y variable and multiple x variables. And also when you have no y variable, but multiple x variables is also a very common case that we're going to see here, why that is. All right, so yes, Comfort.
Yeah, so I have a question with the last one. When you have y1 plus y2, does it mean like they are both dependent on each other or they are distinct, like the response variables?
Yeah, so the way that that this analysis would work is it would still explain each of them separately using the X variables, but it would also allow for the correlation between the Y variables to be incorporated into the analysis, which is something that if you do just one of them, just one Y variable, then you're not allowing for that to be incorporated. Yeah, so the difference is mainly there. You're allowing for those two Y variables for information to be derived from the combination of both of them rather than just each one of them separately.
Oh, okay. Thank you.
Thank you. Okay, so when should we use a multivariate analysis? So normally it would be, and this is what you're going to see mostly in this course, is going to be when you have many predictors that you want to use to either explain or predict another variable. So that is one of the situations. And then the second case here is when you have all these predictors that you want to find groupings among them. So I want to understand, well, of all these predictor variables, are there natural groups that occur in this data sets? So we're going to be applying that as in an exercise called k-means, but something that I was thinking, that perhaps is a good example of how we can think of like finding groups that are underlying groups that exist in the data, but that you may not know what they are or how many there are. So one thing that I was thinking is imagine that you have that nitrogen study. So it's an experimental design study that you have nitrogen rates as a treatment. And we know that nitrogen rate impacts yield. That is until a point, the more nitrogen you apply, the more yield you get. So imagine you go out to your field and you have your plots, you measure yield across all of them, and then you make this plot with nitrogen rate on the x-axis and yield on the y-axis, and you see these box plots increasing, just like we saw in class before. But now imagine that for some reason, when you took that data, you or maybe the person that was helping you with that forgot to take note of which plot the data came from. So you really don't know what nitrogen rate gave which yield. So it's all just a point of yield data, but you don't know what was the nitrogen rate. If you knew that you had 4 nitrogen rates in that study, maybe you can ask for a clustering algorithm to find 4 clusters for you. Most likely, those 4 clusters are going to be very closely related to your nitrogen rate treatments because you're expecting that your yield data has that underlying structure of being affected by nitrogen rate, and you had 4 rates, so 4 groups. So that perhaps is one easy example to connect both experimental design and clustering in this context. So clustering is going to help us to find groupings within your data that you may not know that they are there. You may not even know how many are there, but you are trying to see if there are clusters of variables or of observations that look alike across different variables. So that's when, and also we can use multivariate in this case. And although it could be related to a experimental design, but commonly multivariate analysis are not necessarily like your experimental design model. Like, well, I guess let me take one step back. Let's say that you did have a design that had like a 4-way factorial. That ends up being a multivariate analysis that is related to that design, but it's not like you're bringing all sorts of variables possible to try and explain something, which normally is what we would see in these types of multivariate analysis, especially when it comes to machine learning approaches. So although you could have a design study that is a multivariate analysis because it has so many X variables, because your design was complex, but most of the time we see these approaches that we're going to be talking about, especially on data that is not coming directly from a design experiment, but more of a exploratory or observational type of approach. So with that, there may be a few main types of multivariate analysis overall, but then also that we're going to be seeing in this course. So one of them is going to be dimensionality reduction. So this, as the name implies, is basically necessary or used when you have many dimensions. And what is a dimension? Is basically a column in your data frame. So we have multiple dimensions. We have 72 dimensions in our data. So that's definitely one case that we could apply dimensionality reduction to our data frame if needed and if we wanted. One example, perhaps the most popular example of dimensionality reduction analysis is principal component analysis, or PCA. We're going to be running that as part of this exercise, so we're going to see an implementation of that. A few other examples are principal coordinate analysis and factor analysis. We're not going to be running those here, but if you're interested, if you just Google, factor analysis in R, you're gonna be able to easily find some tutorials that can provide you with the code for that. All right, so dimensional reduction is basically I have all these 72 variables, all these 72 dimensions, and I'm trying to understand if there are fewer dimensions of the data set that I can use and not need to basically give a model 72 x's. Maybe I can just give 4 x variables that are the principal components of that data. Now with clustering, again, it's another main type of multivariate analysis where our goal is not to decrease dimensions, but to create or find groupings of observations across all these variables. So a very common one is called k-means. That is one that we are not going to be doing live in class, but I have an exercise for you to watch a video and code along, and then do an assignment based on that. So you're going to learn k-means, just not live with me in class. You're going to watch a video from a previous term. So k-means is one of them. There are others, like there's c-means, there are x-means. There's other types of clustering algorithms. But basically here, these clustering algorithms, at least the ones I'm listing, they do not take a y variable. They only take x variables. And we're going to talk a little bit more about this in a second as well. A couple of other examples here is non-numerical multidimensional scaling and nearest neighbor. So these are all clustering types of algorithms that we use when we're trying to create clusters or groups or zones within our data. And then finally, the last category here would be when we're trying to establish the relationship between variables and or to create predictive models for prediction. So a few examples here would be multiple linear regression or stepwise regression would fall into this category. Random forest, a very popular machine learning algorithm that we're going to be learning in this class, is also here. And then I have conditional inference tree, which is another machine learning tree algorithm that we're also going to see here. And of course, these lists are not even close to be a full list of all the options. These are just some examples, but really there's a lot of other algorithms that would fit into any of these 3 categories that you could explore as well. And I guess I'm just highlighting here in the using the markdown notation for bold, just the ones that we're going to be seeing in this class, so you know what to expect. Okay, so then there's a few different ways that we can characterize a given multivariate analysis. And so one of them is going to be based on the goal of that analysis. So if your goal, again, here is going to be to decrease the number of dimensions. And when we get to PCA, you're going to understand better why you would like to do this. Like, why do you need to decrease the number of dimensions in the first place? But so you're going to understand the why in a little later in this exercise. But if that is your goal, then that determines what type of analysis you want. So if you want to decrease the number of dimensions, you would not use a clustering algorithm. You would use a dimensionality reduction algorithm instead, right? Now, if you want to create clusters, you would most likely use a clustering algorithm for that instead of a dimensionality reduction algorithm, right? And then, of course, if you want to establish relationships among variables and perhaps create predictions, you would use a different set of algorithms for that. So different algorithms will help you to achieve different goals with what they can do. Now, this context here is also one that's really key to talk about. So the second way that we can characterize a multivariate analysis is based on whether or not you have a y variable. And this is really important of a concept. So if you do have a y variable, so let's say we have strength explained by weather. Strength is our y variable. That means that this is a supervised analysis. And it's called supervised because you have the variable that you're trying to predict. I have strength. I'm trying to understand what variables can predict strength, but I have strength. So I have that variable. So I'm giving the label to that algorithm. The label is the actual value of strength. So it is a supervised, again, because the learning of the algorithm is being supervised based on the y variable that you're given it, based on that label. So you're going to hear the word label very frequently in machine learning literature. So supervised is when you give the label. In our case, you give strength, you give the y variable to it. On the flip side of that coin, there is the unsupervised algorithms. So unsupervised algorithms is when you do not give a y variable. Perhaps you don't even know what the y variable is. So it would be a clustering algorithm. So for example, in precision agriculture, just to give you an example here, maybe if that doesn't connect directly with what you study, maybe I can try to give another example. But in precision ag, imagine you have a field, like a large field, and we know that there is spatial variability in soil properties. So maybe some parts have more clay, some parts have more sand, maybe the pH changes. Maybe a lot of things about soil are changing the landscape that affect how a crop grows and produces yield. So unsupervised algorithm clustering specifically in precision ag is very common when we create management zones. So what is a management zone? It's basically you give a lot of soil variables to this algorithm, to a k-means, for example. So you give soil texture, if it's sand or clay, you give soil pH, you give soil nutrient analysis, and so on. And you ask for that algorithm to look into all these variables and create zones on your field that have different characteristics of soil. So maybe it creates two zones. One zone that has sandy soil, low pH, low nutrients, and then a zone 2 that has clay soil, higher pH, higher nutrient concentration in the soil. And so this would be a case where you don't even know going in how many zones there is in that field. You just think there may be zones, there may be groups, there may be clusters, and you give all these variables, soil related, to this algorithm, and you ask it to spit out what are those groups. This is basically what unsupervised is. We're going to be applying to our data here with weather data, so it's not going to be a field precision ag type of approach, but nonetheless, we're going to be checking for groupings of site years. So maybe in our case, we're gonna basically be thinking of, are there site years in this data set that have similar weather patterns across the year and across different variables? And if there are those patterns, then a cluster algorithm is going to tell you, this is a cluster of 300 site years that look similar. And this is another cluster of another 300 site years that look similar within them, but different from the first one. That's basically what unsupervised does for us. Also, another distinction here is if a y variable does exist, so if you are doing supervised learning, then we can further categorize that based on what is the type of the y variable. So if that y variable is numerical, like it is for us, then those models would be a regression type of model. However, if your y variable is categorical, then you're going to do a classification exercise. A quick example here, just for you to kind of perhaps imagine. So our variable right now, strength, is a numerical variable, right? It has numbers. It goes from, I don't know, 18 to 28 or something. So it is a continuous numerical variable. Because that is the case, all of the machine learning algorithms we're going to be doing are going to be regression based. However, imagine now that So if we, let me do a quick drawing here. Just to show you how we could create categories out of a numerical variable. So imagine that we have a geom density of fiber strength. Okay, so we have fiber strength here on the x-axis, and then the y is just the density. So imagine we would have like a normal distribution of fiber strength values, right? A numerical variable. Now, sometimes you may want to create categories out of a numerical variable. And one of the ways for that would be to look into quantiles. So you would remember that the 50th quantile is basically your median, right? That is the concept of the median is the 50th quantile. But if instead of the median, well, I guess we can use the median. So you can create categories out of this numerical variable that is fiber strength by first extracting the median and then saying every value that is less than the median, I'm going to call this low strength. And every value that is higher than the median, I'm going to call this high strength. So now you have a new column that instead of having numerical values for strength, you have either high or low, depending if that value was less than the median or more than the median. So now we have this column that has values high and low, the words high and low. Those are categories. That's a categorical variable. You could decide to, instead of predicting the numerical fiber strength, you could decide to train a model to predict the class, if it's a lot low or high fiber strength. In that case, if we were to do that, then our machine learning algorithm would be of a classification type, because you're trying to create a model that classifies an observation in either low or high, instead of then giving you a number of actual strength. So that would be perhaps one example that we can use even the same data set, just creating a new column and either running a regression if you explain fiber as numerical, or classification if you run on this column that is a categorical column that has highs and lows. All right, we just talked about a lot of terms, and I think some of them is going to be easier for you to understand as we start moving through the exercise. But any questions that I can answer at this point? All right, I don't hear anything.
Dr. Bestos,
Yes.
for my research, I use a lot of partial least square regression. So is there any resources that maybe you can share with me privately or in the GitHub?
So we're gonna be running an exercise when it comes to machine learning that is gonna cover some of those topics. So maybe after we go through that, if you still need some more resources, let me know and I can share with you.
Thank you.
Thanks, Rick. Okay. So we have here about 12 minutes, so not a lot of time, but let's try to get some traction here. So I want to ask you that for you to install these packages, these 3 packages. Well, if you have them already, great. If you don't, because I don't think in this class you needed them yet. So if you don't have them, please go ahead and install. So ggcorplot is going to help us to make some ggplots to look into correlation of variables. Facto extra is going to help us to look into some clustering functions when we get to that part of the exercise. And ggp misc just has some functions that help us to add some annotations to a ggplot. Remember, if you are installing them, make sure you just run that line of code. And once you install, either comment it off or just delete that installed packages so you don't have active in your scripts. And once you install all those 3, I don't think it takes a lot of time. But once you have them installed, just go ahead and run the chunk so we can have those packages available for us. All right, so the first thing that we are going to do here is to look into our, or to bring in the weather data that we exported from the previous exercise. So let's do that in this chunk here. We're going to use the function read underscore CSV. In the quotation marks, we're going to have to navigate to the previous project. So // we get outside of code folder. Now another // we get into our main folder of the course. You go inside of the 09 open data project. You go inside of data, and we want to bring the weather month sum.csv. So make sure you import that. And as you print it, you should see the same thing as we exported on the previous exercise, which is basically 698 rows, where each row is related to a specific site year, and then 75 columns where we have year, site, and strength, and then 72 columns related to weather data, where we have a combination of the weather data summary and the month that was summarized over as the column names. Okay, so on this EDA specifically, what I want to do is check to see if there are any strong correlations between all these X variables specifically. And as we're gonna talk more about multicollinearity when we get to that part of this exercise. But if we do have variables that are highly correlated, so weather variables that are highly correlated, that is something we want to be aware of because it could cause some issues depending on the algorithm that we're going to use later. So what I want to do here is to basically calculate a correlation matrix between all those 72 variables. So imagine that we're going to basically do all 72 variables by them. So imagine like a matrix where you have all the variables on the x-axis, all the same variables on the y-axis, and we have just a different correlation value for each one of those intersecting variables in this matrix. So if for to do that, we come here on this chunk, we're going to start off with the data. So weather is the object name. Let's give it a pipe. I want to basically remove the variables year and site from here, just because we're not going to be calculating the correlations for those two variables. We don't care for them. They're just the descriptor variables. So let's do a dplyr select minus year and minus site. So if you just run that, this is basically same number of rows. We just have two fewer columns, which are the ones that are missing year and site. And then you pipe that into a function called core underscore pmat. So this function is going to calculate for us all the potential bivariate correlations. So taking each one of the weather variables by all the others and the correlation for each one of those pairs. If you print this, I mean, you can print if you want to try to see what this looks like. It's really, I mean, all those correlation coefficients, so the R correlation coefficients are in these cells, are for each one of those combinations of two given variables. But because we have so many variables, this output here is just really not useful to look at. It's just a lot of numbers, difficult to make sense of. But all those correlations are here, and that's the key. So we're going to use that to create a plot, that once we create the plot that we can export to file, we can zoom in, zoom out, and really understand what's going on. So if you come, well, I'm going to do this. I printed pmap, but if you print it, it's going to be a lot of scrolling for you. If you don't want to do that, just close this output window, because we know already what that is. We just know that it's too much going on right there. So I left you the code here for the next chunk. So we're starting with the weather data frame. We're removing year and site the same way. We're piping that into this function core, which if we just run until here, it should be a pretty similar output of the first one. And then we're feeding this into a function called ggCorePlot. I'm not going to walk you through everything that's going on here on the argument side of this, but this function is basically going to create a matrix heap map of correlation across orbit among all of these variables. So if you run this, it may take just a moment to go through. This is what it looks like. Of course, like this is also not very useful for us to look into R. So if you do that ggSave, it's going to export this to file with the dimensions that I gave here. And that I'll be with you just in a sec, Tifton. And then if you go in your file, so if you go on output and you look at Cormat, it's this plot. So you could, what we have here is basically all the 73 variables, so all the 72 weather plus strength. We have them both on the columns, on the y-axis and on the x-axis, and then we just have all the correlation between all of those variables. So a lot of correlations here. And then each cell, if you were to zoom in, so let's say, so correlation, so this is the R, correlation coefficient is R, it's not R squared, meaning that R ranges from -1 to 1. And then we have them color coded as well. So if it's near to 0, it's going to be white. And if it's negative, is blue. If it's red, if it's positive, is red. And you can kind of look for those patterns. So let's say if we were to look specifically here, let's see where fiber strength is. Fiber strength. Right here, right? So if we were to look just at fiber strength, which is our y variable, and you would just go up this column, and we see what are some of these strong correlations here. I think I'm seeing a 0.2, a couple 0.2s here. So doesn't seem like any one of these variables by themselves are explaining a lot of fiber strength, which is expected, right? But let's say if you were to spot one of the variables here, like, oh, I see there's a -0.2 here. I want to see what is the variable that in relationship with strength is a negative correlation of 0.2. You would just basically come on this matrix all the way to the other axis and see what is that variable. In this case, it's mean solar radiation in September. So it looks like as mean solar radiation in September increases, fiber strength decreases because it's a negative R. So again, this is a huge correlation matrix because we have so many variables, but that is one of the ways that we could use to inspect some of those correlations. Tifton, let me go to you now. Do you have a question?
Yes, I'm having an error for the previous chunk. For the core PMAT, yes. I ran that chunk and it's saying the X must be a numeric vector. It's giving me an error saying X must be a numeric vector.
Did you do the select -0 minus height?
Yes, I did.
So what could be happening if to give you that error, it basically means, so yeah, core PMAT only takes numerical variables. So and that was the reason why we remove site, for example, because site is not numerical. So what I would do, Paulie, is like print just until here and look into your variables and make sure that they're all double. You could also do that if you just connect this to a glimpse. Glimpse is going to tell you, oh, hold on, that didn't work. Maybe didn't like that I put in an object, I guess. But if you do this and do a glimpse, it's going to give you a list of the variables. They should all be numerical. They should all be double. I'm guessing that for some reason, one or more of your columns are non-numerical, and that's why it's giving you that error. So, Paulie, take a look at that. If you continue seeing issues, you can open an issue on GitHub, and maybe someone else can also weigh in, and I'm in there myself as well. But because we're getting to the end of our class time, I do want to wrap things up here. So So I guess the point that I wanted to wrap up is just that we created this correlation matrix to look into those bivariate correlations between any weather variable with any other weather variable in strength. And we saw, well, I guess we're going to have to come back to this chunk in the next class just to interpret a little bit more what that plot is telling us. So just make sure you save your script. Aminder, have you opened the, okay. So Aminder already opened the attendance issue on GitHub. Make sure you claim your attendance. And then once you do that, you're dismissed. I'm going to stick around for a couple minutes in case anyone has any questions.